welcome to today's Explainer. I am absolutely thrilled to have you here because today we are tackling one of the most massive, consequential questions of our time. How do we find enough clean energy to literally suck carbon right out of the atmosphere? We know we have to remove greenhouse gases to hit our climate goals, but the mechanics of powering that removal process, they are incredibly complex. So today, we're going to explore how the Earth's very own internal engine might just be the silver bullet we've been looking for.
Think about this for a second. What if the very pollution destroying our climate could actually be used to generate clean electricity? It sounds a bit like science fiction, right? Like some sort of thermodynamic magic trick? But as we dig into the research today, you're going to see that this isn't just a wild theory. It is cutting-edge engineering that is fundamentally flipping the script on carbon waste.
We've got a lot of fascinating ground to cover today. First, the carbon capture energy problem. Second, geothermal to the rescue. Third, integrating geothermal and DAC. Fourth, the CO₂ plume innovation. Fifth, real-world global CCUS projects. And finally, the climate bottom line. Let's dive right in.
Section 1. The carbon capture energy problem. The hidden cost of direct air capture. Okay, so we've established that reducing emissions just isn't enough anymore. We have to actively remove the CO₂ that's already sitting up there in the atmosphere. But doing that is incredibly tough because CO₂ is highly dilute. We're talking about 420 parts per million. It's literally like looking for a needle in a haystack. So how do we power the massive machines needed for direct air capture, or DAC? Because if we power these machines with fossil fuels, we're just emitting carbon to capture carbon. It makes no sense. We desperately need a massive zero-carbon energy source to feed this ultimate energy hog. And just how much of an energy hog is it? Try 2,000 kilowatt hours. Current estimates show that scaling up direct air capture could require up to 2,000 kilowatt hours of energy just to capture one single ton of CO₂. To put that into perspective, that is enough power to run an average home for months just to grab 1 ton of gas out of the sky. But here's what's really interesting about that energy demand. It is not all electricity. In fact, 80% of the energy required is thermal energy, just pure heat. Only 20% is electrical. Why? Because a lot of DAC systems use these solid sorbent chemicals to grab the carbon. Once that chemical sponge is full, you have to heat it way up, usually between 80 and 120 degrees Celsius, to bake the pure CO₂ out and regenerate the sorbent. So the big takeaway here is we don't just need clean electricity. We need a massive, clean source of heat.
Section 2. Geothermal to the rescue. Earth's built-in battery.
This is where geothermal energy steps up to the plate as the absolute hero, providing both the thermal heat and the electrical power that DAC desperately needs. To understand this, we've got to look at a binary geothermal power plant. This is a system that uses super hot underground brine to heat a secondary fluid in a closed loop. That secondary fluid vaporizes, spins a turbine, and generates electricity. And this part is absolutely crucial. Unlike older steam flash plants that vent steam and trace gases into the air, binary plants are totally pressurized and sealed off. They emit absolutely zero CO₂ during operation. We just extract the heat, make the power, and pump the liquid straight back into the earth.
Section 3. Integrating geothermal and DAC. Wiring carbon capture into the Earth.
So now we have a totally clean energy source producing heat and electricity. Let's look at how engineers can physically wire these two technologies together to get the most bang for our buck. One option is a parallel configuration. Step 1. You bring up the hot geothermal brine from the well, and you literally split the pipe. Step 2. The main stream goes to power the turbine, generating grid electricity and running the DAC fans. Step 3. You send a smaller slipstream directly into the DAC unit. That hot fluid acts like a giant radiator, delivering that crucial 80 to 120 degree heat to bake the carbon out of the solid sorbents. It is pulling double duty, all at the exact same time.
But what if we don't split the pipe? What if we run the whole thing in a series? You've got upstream and downstream options here. In an upstream model, the hot brine hits the DAC unit first, and the remaining cooler heat goes to the power turbine. But the downstream configuration, well, this is where the magic really happens. The hot brine runs the turbine first, squeezing out the highest grade heat for electricity. Then the leftover waste heat, which conveniently sits right in that 80 to 120 degree sweet spot, flows directly into the DAC unit to regenerate the sorbents. It's like squeezing every single drop of utility out of the Earth's energy before pumping it back down.
Section 4. The CO₂ plume innovation. Flipping the script on pollution.
Now, as amazing as that is, the engineering goes even further. We're looking at a breakthrough where we aren't just capturing carbon, we are fundamentally rewiring how geothermal power works from the inside out. The AdTerra consultancy actually describes this as transforming CO2 waste into clean energy. They're talking about a revolutionary concept called CO2 plume geothermal technology, or CPG. Invented by researchers at ETH Zurich, this takes carbon capture and storage to an entirely new level.
Let's compare standard geothermal with CPG. Standard systems use natural underground water or brine to carry the heat up to the surface. But CPG? It actually injects the very CO2 we've captured from the sky deep underground and uses that CO2 itself as the fluid to bring the heat up. Because CO2 flows easier and expands differently than water, it can actually generate over 2 times the power of a conventional water-based system. And the kicker? As it cools down after spinning the turbine, it gets denser, and we just re-inject it back underground. We are securely storing the carbon permanently while generating massive amounts of clean power. It's incredible.
Section 5. Real-world global CCUS projects. Grounding theory in reality.
Now, you might be sitting there wondering, okay, but is anyone actually moving millions of tons of CO2 around underground today? The answer is absolutely yes. Carbon capture, utilization, and storage is not just some academic model. In Western Australia, the Gorgon project is capturing and injecting 3.4 to 4 million tons of CO2 every single year, over 2 kilometers beneath the surface. Over in China's Jilin province, they're injecting 600,000 tons a year. The know-how and the infrastructure to transport and securely lock away millions of tons of carbon into geological formations, it's already happening globally.
Section 6. The climate bottom line. The abatement multiplier.
So we've looked at the tech, the thermodynamics, the global scale. Now we have to ask the big question. What is the actual net climate benefit of marrying a binary geothermal plant with a direct air capture facility? Does the math actually work out? The answer is a massive, resounding yes, up to 757%. Researchers ran the numbers, and they found that if you take a standard geothermal plant that only makes electricity and you integrate direct air capture using that downstream waste heat, you increase the plant's total CO2 abatement by up to 757%. You are knocking fossil fuels off the grid while actively ripping historical carbon right out of the sky at the exact same time. It's a massive abatement multiplier.
Of course, we do have to talk about the economics. The levelized cost of energy delivered to the DAC system ranges wildly, anywhere from $101 to almost $8,600 per ton of CO2. So why the huge gap? Well, it depends on the heat of the reservoir and the setup. You get the best, most competitive costs when you pair really hot reservoirs with that downstream setup using sorbents that don't need as much heat to regenerate. Also, drilling is insanely expensive. But here's a thought. The U.S. alone has 3.7 million abandoned or orphaned oil and gas wells. Repurposing those existing holes in the ground for geothermal energy, that could drastically slash upfront costs and make this highly viable.
As we wrap up, I really want to leave you with this final provocative thought to chew on. Will the very pollution that threatens our surface be the key to unlocking the boundless clean energy beneath it? By turning CO2 into a high-efficiency working fluid for geothermal power, we are literally taking our past mistakes and using them to power a clean future. The synergy between the Earth's natural heat and our advanced capture technology is just undeniable. It offers a genuine, logical path forward. Thank you so much for joining me on this explainer today, and keep exploring the incredible science that's shaping our world. See you next time.